today we're going to be talking about the plasma geometry in the solar system and beyond, but I kind of set myself up with this title because I've sent it like a couple of months in advance, but really we're going to be talking mostly about plasma, not less about geometry, even less about the solar system, okay? I hope you don't mind. So, a lot of the things I'm going to be talking about I've already presented at this recent conference in Albuquerque, Electromagnetic Structures from Micro to Macro. So you can find on YouTube some recording of it, which we did with some friends in Skype. So there's a lot more details, okay? And some more details are also available at the recent videos that I did for the Thunderbolts Project YouTube channel, these recent space news videos. So this talk is going to be only a brief abstract, and you'll find more details there. And I should also say thanks to Jim Wenninger, because a lot of what I'm going to be talking about is really his ideas, so don't reference me as the author of the idea, unless stated, let's say. And I would also like to say thanks to Robert Farrar. He's actually from the UK, and his topics on Thunderbolts.info forums have actually inspired me in the last couple of months to research more and more into this problem, let's say. Okay, so the main idea that we're going to be dealing with here is the hypothesis that the plasma currents might influence the behavior of celestial bodies in a major way, okay? So I believe that if we start from this idea, okay. So I believe if we start from this idea, then we really have to solve pretty much simultaneously two tasks. So we would have a theoretical task, which is to develop a model of how the plasma currents actually, well, kind of should behave theoretically, right? According to Maxwell's equations or some other, I don't know, type of physics that we would use. But we should also solve the observational problem at the same time to try to identify in space the structures that might represent these plasma currents, all right? And I think that these tasks should be solved simultaneously because, well, we have no idea what can happen in space, right? So we need the observational part. And at the same time, we really have very little understanding of plasma physics at the moment, so we also need to develop a theoretical part. Okay, so here we're going to be, I'm going to briefly describe the theoretical part in this presentation. Then we'll talk a bit more about the observations that could provide us hints at indeed the interaction of the solar system, let's say, with the interstellar medium. And then I'll talk briefly about some recent findings that I've had with regards to this problematic. And then we'll talk about Plasmascape, but I won't tell you what it is right now, so you would have to wait, okay? So we'll build some tension. And I have to note that this is a research program. It's not a collection of results, so what I'm going to be talking about is more like a vague horizon with some silhouettes here and there, right? So some vague evidence. It's not a complete theory, let's say. So without further interruption, let's celebrate and have some fun. So, theoretical part. Now here, I think we might say that Don Scott really did a great amount of work recently, in the recent years. So here I've given you a couple of his papers where he has derived a model following some earlier works by Stig Lindquist, for example, of how the plasma currents should arrange themselves, what kind of structures they should form. And here are some of the illustrations from his papers, but I wouldn't really use those. Rather, I would actually use the illustration produced by James, who's been the speaker yesterday and is going to be speaker today also, right? So I say thanks to him. So this is the link to this visualization, and it's actually animated there, and it's interactive, so you can play with it. So this is the model of Don Scott's type of plasma filament, essentially. So what we can see here, and okay, probably one of the most important properties of these currents that Don Scott is describing is that they are Birkeland currents, which means they are field-aligned currents. So in each point in space, the direction of the electric current is parallel to the direction of the magnetic field. So basically, you can treat those as the direction of a current or a magnetic field because they're the same, essentially. So, and we have this peculiar structure where we have those sort of like embedded cylindrical shells of current, where at the axis of the current, you have the current just flowing straight, But as you go farther away from the axis, it starts to kind of spiral around a little bit. As you go even farther, it spirals more wildly. And at some distance, it would actually become circular. So you would have like a tube of circular current. But then it actually, at some bigger distance, it slightly reverses and starts spiraling, et cetera, et cetera. And at some distance, it would actually reverse completely. And so you have this weird system. And well, Don Scott actually solved his model for infinite cross-section. So you have pretty much infinitely many of those cylinders, right? But of course, in real life, we would have to somehow adapt this model because we always have some boundary conditions, right? And that might actually theoretically introduce some, I don't know, some other unknown phenomena. But this is a good starting point, I believe. So one takeaway that you should really remember from this visualization is that we have embedded cylinders with current direction, which is reversed at some points, all right? So, and we also have to take into account the idea of scalability of plasmas. Like, for example, introduced by Hannes Alfvén in his paper on hierarchical cosmology, this idea of cosmic triple jump, where, well, this is basically the idea that plasma on all scales behaves pretty much in the same manner, right? So in the laboratory, we can study cosmic processes, therefore. And I've also proposed to enhance this scheme during my recent presentation to cosmic quintuple jump, where we also add steps downwards to the atomic scale and subnuclear scale, because I believe that phenomena that we observe at these scales also can be explained by electromagnetism, all right? But this is just the idea of scalability of plasma. And we can pretty much conditionally subdivide the scales that we observe around us into those steps. Of course, this is very arbitrary, so you can choose different scales, but I believe this is the reasonable choice. So we have the scale of the solar system, which is less than 1 light year, even less than 0.1 light year. If you, well, that depends on what you consider the boundary of the solar system. We have the scale of the local interstellar cloud, which is tens of light years, and the scale of the so-called local interstellar chimney, which is even bigger, about 1,000 light years. And then we have the spiral arm, and then we have the whole galaxy. But in this talk, I'm going to be focusing on these first 3 ones. And we'll start actually from the largest one, this local interstellar chimney. So the idea is, according to mainstream astrophysics, what these chimneys are, is that we have supernovae somewhere in the galactic disk, but since the galactic disk is very dense, there's a lot of stars, a lot of stuff there, so this supernovae material cannot expand a lot into the galactic disk, so instead it expands upwards from the galactic disk and downwards. Well, here you have a couple of examples like that. And so this expansion, it produces this, what they call hot coronal gas, which is, of course, only a politically correct term for plasma, right? That would fill the galactic halo, etc. But our idea here is that these chimneys, so it looks kind of like a house with a chimney, you know, and the smoke is coming on the top. So hence the name, I guess. But anyway, our idea of me, Jim Wenninger, and others, that these chimneys might actually represent a Birkeland currents, okay? Especially if they're simultaneously up and down, because that's also what we observe. So here are the couple of papers that describe our local chimney, where we are situated. And the third paper I quote here is, it actually describes some other chimneys some 10,000 light years away from us. So it's not a unique phenomenon. It seems to occur pretty much everywhere in the galaxy, right? So this is a section of our local chimney. The sun is in the center. The galactic center is to the right. And so it looks pretty much like a tube. Well, at first approximation, let's say, as a cylindrical tube. So this is one of the indications that this might be Don Scott-ish type of plasma filament. And if you look on the top or to the bottom, you would see, of this chimney, you would see these darker areas. So there's not much of neutral material there. This is in the galactic coordinates, the absorption of light, essentially. But when it's lighter, it's actually more absorption, okay? So darker areas means less absorption, so there's less neutral material on the axis of the chimney, in this tube, basically, which means there may be more ionized material. So maybe there's a higher current strength. This is the idea, okay? And another interesting feature of that object is that there is so-called Gould belt, a toroidal belt of bright stars, star-forming regions, molecular clouds, etc., wrapped around this cylinder. This is the depiction of the Gould belt, again, in galactic coordinates. And in general, the whole structure of this hourglass-shaped chimney, plus the Gould belt around it, resembles pretty much the famous Perrat Squatterman or Stickman figure. So it might be the evidence that this is actually some sort of plasma discharge, right? Okay, so let's go on a scale lower. So here we can see the local interstellar cloud. So this is, again, the scales. Well, you can see the distance in light years, so about, let's say, 40 light years in size. You can see the sun in the center, some local stars, Alpha Centauri, Sirius, etc. So this is actually an artist's impression, but it's based on real data. So it's more or less accurate, let's say. Okay? But if you look at it in more detail, what you can see there is that there are kind of darker regions in between those clouds. And I've had an idea recently that maybe it's those darker regions that actually represent plasma filaments. But the clouds themselves, they serve like an insulator for this current, right? And so if you compare those two pictures, let's say we have two filaments dancing around each other in such a way, I think that would make sense, but this is only a hypothesis at the moment, okay? But we've observed such structures in other places, like, for example, the so-called double helix nebula that you can see here. And it's peculiar that the authors of this paper, for example, this is also basically a two plasma structures wrapped around each other. So the authors also state that the axis of the structure is roughly perpendicular to the galactic plane, which is also the case for our local chimney, for example. Okay, and they themselves state that this is possibly a part of larger structure. So again, this idea of scalability comes into play. So it's filamentary, my dear Watson. Now, I've already used that picture, but since I'm in the UK, why not use it again, right? So, the question might arise, like, if there are so strong currents, why don't we see them, okay? So there are certain considerations that we might use as an answer to this question, like, for example, on the scale of the solar system, if we're using space probes for measuring, let's say, the electric potential, right? So how can we even measure any potential difference with a small space probe? It's going to be, almost by definition, it's going to have the same electric potential as the plasma around it, because the plasma is almost like a perfect conductor. So whatever, you're not going to measure anything, right? You have to have some potential difference. This is one point. And we cannot directly measure the potential between, let's say, the orbits of Earth and Mars. This is just technically impossible, right? Another point is that well, you can say, well, we should have synchrotron radiation from particles moving in these magnetic fields. But if the electric current is parallel to the magnetic field, as I've said, the currents are field aligned, we wouldn't have any, well, virtually any synchrotron radiation, because the particles are not accelerated. They're just kind of, just in a very relaxed manner, move along the magnetic field lines, and that's it. So we wouldn't see also the synchrotron radiation. And the Faraday rotation, which is frequently used to map the magnetic fields in space, so Faraday rotation is an effect of turning of the plane of polarization of light in a magnetic field. So by observing the polarization of light, we might it's a secondary tool of measuring the magnetic field, essentially. But if we have those cylindrical shells of oppositely directed currents, each consecutive shell would cancel the Faraday rotation from the previous shell. And in the end, the best you can find is some weaker background magnetic field that this filament might be moving along. So you wouldn't detect that also. So this is kind of counter-arguments to this point that we should see those currents. Okay, so let's examine some other structures around us that might serve as an indication that we really interact with interstellar medium in an electromagnetic way. So this is the so-called Ibex ribbon. It's a pretty famous structure. So this is the map of the sky, all right? And what is mapped here is the flux of, that's the amount of particles of so-called energetic neutral atoms, ENAs. So what that is according to mainstream, again, astrophysics, it's the solar wind ions that go to the edge of the heliosphere. They're positively charged, right? But then they catch electrons there from the interstellar medium and fall back towards the sun, and that's where we catch them, right? So it's essentially an electric current flowing from the heliosphere to the interstellar medium, if you take into account the regular, if we consider the direction of positive charges as the direction of the current, right? Direction of motion. So we see this structure, which is called IBEX ribbon. IBEX is the satellite interstellar boundary explorer that have found this. And it's actually the circle in the sky. It's just in this projection, it doesn't look like a circle. So it's like we have a heliosphere, a sphere, and its section with some plane would be a circle. So that would be the IBEX ribbon. And one of the interesting features of that structure is that it changes with the solar cycle. So at solar minimum, you can see on the left, on top left here, 2009, that was pretty much the solar minimum. It's much more pronounced, much more intense, but then it kind of fades away as we move to the solar maximum. So that shows us that solar activity is not only about sunspots, the whole heliosphere is affected by it, right? Or you can think about it in reverse. You can say that it's the changes at the boundary of the heliosphere that cause the changes in the sun, right? But, well, it's so far I would say it's not a definite proof, but there is something there, that's for sure. So if you weren't convinced that the IBEX ribbon is circular, here's the picture from this paper where they use the coordinate system actually centered on the center of this structure. So you can see it's pretty circular. All right, and there's another structure like that that was observed by Cassini probe that was already mentioned today by Wall, which Cassini observed the same energetic neutral atoms, but at higher energies. So IBEX was about 1 kilo electron volt, and here we see 5 and higher. And Cassini also found other structure of the same sort, also like a belt around the solar system. And it's interesting that the IBEX ribbon and Cassini belt are kind of displaced with respect to each other, so there's some complex geometry going on. And there's a lot of debate right now whether even, in the astrophysical community, whether they are part of the same structure, whether they are of different origin, et cetera, et cetera. And actually, I can tell you from reading those papers that IBEX team kind of disagrees with Cassini's team, because IBEX, even about the shape of the heliosphere, like IBEX researchers are convinced that the solar system has a long tail, whereas Cassini team claims that no, it's actually very spherical, there's no tail at all, or something. So there's a very interesting debate going on right now. So other structures, other observable data that we can use in our approach is, for example, cosmic microwave background. You probably heard about the theory of Pierre-Marie Robitaille that monopole of cosmic microwave background might come from Earth, but I'm not going to be talking about that. Rather, I'm going to focus on dipole and multipole components of CMB. So dipolar components, it means that basically we have a hot pole somewhere in the sky with slightly higher temperature, and we have a cold pole in the opposite point of the sky, right? And multipole, it means we have many hot poles and many cold poles, so it's a much finer structure can be traced. So in this paper, the authors state that the direction obtained from optical polarization data mimics the symmetry of the dipole moment of the cosmic microwave background. Now, the direction that they talk about here is actually the direction of the interstellar magnetic field. And I can actually tell you exactly how it's oriented. It's perpendicular to the dipole of the cosmic microwave background. And this might be something to study, like maybe dipole of CMB is actually not related to cosmology at all. It might be related to our local interstellar environment. And the same thing can be said about multipole. You probably, I don't know, maybe you've heard about Gerrit Verschuur, who has found that the multipolar component, at least in some portions of the sky that he actually studied, correspond to neutral hydrogen emission morphology. So they might be these multipolar specks that we observe might be actually related to some, I don't know, interstellar clouds or something like that, and not cosmology. So that's another thing we might use as observational data. So okay, there's a lot of other stuff to talk about here. I'll just briefly mention all those points. So there is a problem with measuring of parallaxes on many occasions, and these are probably the most famous examples, like Pleiades parallax. There's some anomalous readings there. Polaris, the pole star, the same problem. But okay, so what parallax is we're observing a star at the angle at which we see the star in some point of our orbit, but then we move half a year after. So Earth has moved in its orbit, so it's slightly in a different spot like, let's say, in the local environment. And we observe the same star, and the angle slightly changes, right? So from this angular difference, we can derive just geometrically the distance to the star. It's very easy to do. But it turns out that these parallax readings are not really consistent, at least for some objects, with respect to other methods of determining the distance. And again, the famous example is Pleiades. It's pretty much a model star cluster. And Polaris, the pole star, it's the closest Cepheid variable. So we need all that to determine the other distances. If we don't know the distance to Polaris, I mean, Cepheid variables, they're used to determine the distances. So if we don't even know the distance to the closest of them, so everything breaks down pretty much, etc. But in our framework of plasma currents, we might say that there are works, like for example, the paper quoted here by Dr. Gupta, but the works of Dr. Dowdy, that claim that actually the refraction of light in plasma might bend the direction of propagation of light. So if we assume that there is some plasma structure in between us and whatever object we're observing, it might screw the parallax readings quite a lot. So this is the idea, all right? Then we might derive some other observational data from chemical compositions of stars. Now, of course, there's an idea that there might be transmutation or something like that, but even without it, so this is a couple of papers that talk about the various anomalous readings of chemistry. And so one of those papers, this one, actually directly states that we present evidence that anomalies in abundance of the chemical admixtures, blah, 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 can be related to a topology of the large-scale magnetic field. So, yeah, they actually admit that it might be some larger-scale magnetic structures that are, let's say, predetermining these anomalies. And, of course, in the EU context, there is an idea of Markland convection, of the sorting of chemical elements according to their ionization potential in the current column. So this might be another instrument how, at least potentially, we might explain some of that anomalous chemistry. And then there are some anomalies in temperature estimates of stars. Here's a pretty fascinating graph of Arcturus temperature, which you can see it's pretty much linearly rises, right? From about 3,800 to about 4,600 or about so in only like 80 years. And this is like insane. It shouldn't happen according to, you know, our stellar models. So, but if we assume that the stars actually are powered or at least influenced externally, then just the motion of Arcturus with respect to whatever the current was feeding it can cause the change in its temperature and its brightness, right? Plus, we have multiple accounts of some ancient astronomers referring to Sirius as a red star. But if Sirius was previously in some, let's say, it was a bit farther from the axis of whatever current is feeding it, but then it moved closer, it might become brighter and more blue, like it would have higher temperature, etc. So this is also potentially an explanation for that. And you can see here that Sirius is actually pretty close to what I hypothesized to be this darker filament, right? The sun is actually also pretty close, but, well, we don't really know that with much accuracy, let's say, but this is an idea at least. Okay, then we have blue shifts and red shifts, which are frequently used to measure velocities and distances, etc. And of course, there's an idea of intrinsic redshift by Halt and Arp, but I wouldn't talk about that. Rather, I would mention that there is evidence, there is both experimental and theoretical evidence that plasmas can actually lead to both red shifts and blue shifts of light, right? This is on the bottom. It's a very interesting paper that talks about the redshift in plasma. Okay, so this is a very interesting paper. And by the way, I've already petitioned the UN to consider the full bibliographic record of this paper as a crime against humanity. So that's why I give to you in full. So this paper described the measurements of the magnetic field on Earth's orbit. So these circles are Earth's orbit. So we measured the solar wind magnetic field averaged over, I don't know, 3 months intervals or something, or 1 month intervals. And these are the directions of the magnetic field. So, of the solar wind, or at least supposedly. But what they found was that their analysis confirmed the existence of the large-scale background interplanetary magnetic field, BIMF. And this BIMF does not correlate with the sun. It means it might not even be related to the sun in the first place, okay? And even more so, they found that there is a vortex structure of this BIMF. So there's a circulation of the magnetic field strength vector along the Earth's orbit, at least. And this circulation, if you just use Maxwell's laws, it would correspond to a current of gigaamperes, 10 to the 9th amperes, within the Earth's orbit. So there's a current either, I don't know, directly perpendicular or at some angle, but there's a current running there. And we can measure that, at least through those secondary means. And they also found the evidence of solar activity being a complex phenomenon of the solar system as a whole, again, as I've already mentioned with regards to IBEX data. Okay, so this is Voyager data, Voyager 2. It measured the speed of the solar wind on the top, the density in the middle, and the temperature at the bottom. But the thing I wish to mention here is that, well, look at, for example, the graph for the velocity of the solar wind. You can see that there are very distinct peaks here and there, at roughly from 20 to 60, let's say. It's the most prominent region. So if we remember Don Scott's model, it has all those cylindrical shells of embedded currents. So maybe this is actually the evidence of Don Scott type of filament in the solar system. I don't know, but this is the data that we can at least use in the future. So there has been a lot of stuff that I've missed here, and I would probably even not mention what I've missed because, well, there are some time constraints. But again, I would refer you to those videos that I did for the Thunderbolts and my previous presentation at the OTF conference. Let's talk about the recent findings, like some interesting stuff that I found myself recently while being inspired by Jim Wenninger's ideas. So here you can see the orange plane is the solar equator plane, blue is the galactic plane, and orange arrow is the solar spin axis, okay? And I've also marked the direction to the galactic center and vernal equinox, okay? And there are planetary orbits also. So you can see that the solar equator crosses the galactic plane at some line. Well, that's not a big surprise. It should be that way, right? But what if I plot here the direction of the interstellar magnetic field that is taken from IBEX data and local chimney axis, which was taken from the papers I've quoted before? So what if I'll just draw a plane through these two, interstellar magnetic field and local interstellar chimney? Where do you think it would cross the solar equator? It actually turns out that it's the same line. And I think it looks important, actually, because if you take 3 random planes, they shouldn't cross at the same line. Like, think of the coordinate planes like XY, YZ, and XZ. They cross in perpendicular lines. But here you have some weird arrangement. So from my perspective, it actually looks like the solar equator is not aligned randomly with respect to the galactic plane and these other structures, like the local cloud, local interstellar chimney. It looks like it actually makes sense on some level, right? Well, that's a good thing. Okay, so let's talk about this supposedly interstellar asteroid, Oumuamua, right? So on the left, you can see the real image taken by Hubble Space Telescope. On the right, you can see, I don't know, like artist's impression, but just, in fact, there is evidence that it might be not of that shape, but of a pancake shape. So it might actually be misleading and harmful. So don't believe that. All right, so I've made quite a bunch of videos for Thunderbolts, again, on this topic. There's a lot more details there. But here I wish to mention at least one thing that I found, and it's that the plane of the orbit of this supposedly interstellar asteroid, its hyperbolic orbit, actually the interstellar magnetic field vector lies with a pretty good precision, like maybe a couple of degrees difference, in the same plane, in the plane of orbit of this interstellar asteroid. So I've also had a hypothesis that it's not interstellar in the first place, because during its perihelion, the sun was very active. Like, it produced the strongest solar flare in 12 years. It was September 2017. So I had a hypothesis that maybe it's actually the sun that's produced this object during one of those flares or whatever. That would also kind of make sense, at least to me. And it wouldn't be surprising in this case if why is it orbit aligned with interstellar magnetic field, because if the solar activity is driven by the interstellar processes, that would make sense, right? Or if this object is indeed an interstellar asteroid, then it probably spent a lot of time in the interstellar medium, so that's why its orbit is aligned with interstellar magnetic field, right? But this would also mean that we don't understand how bodies move in interstellar medium, okay? And there are a couple of other interesting things that I found, like, for example, if we take ecliptic longitude, that is in the ecliptic coordinate system, just the longitude. So again, I've made another video for Thunderbolts about Planet 9 where I describe this in more detail, but here I just briefly mentioned that there are so-called detached trans-Neptunian objects, detached TNOs, which means they have a perihelion of more than 30 astronomical units that is beyond the orbit of Neptune, but semi-major axis of 250 and more, which means their orbits are so big that they are not really connected to planets in the first place. So planets cannot influence their orbits in any major way. And so the authors of the paper that I use in that video actually claim that this is the evidence of another planet that has clustered these orbits in such a way. Yeah, but the paper talks about the clustering of orbits of these detached objects around this 73 degrees longitude, right? But what I've noticed is that the interstellar wind that we can observe in our solar system, as for example the so-called helium focusing cone, but okay, disregard that. But the longitude of the interstellar wind is pretty close to that. It's 75 degrees. And even more so, like solar equator ascending node, the line where the solar equator intersects the ecliptic, the orbit of Earth, is 76 degrees. And the perihelion of Mercury is 77 degrees. So it almost looks like the whole thing, the whole system, starting from the sun itself to those detached objects, is somehow aligned with respect to the interstellar structures, right? And by the way, the longitude of interstellar wind actually shifts slightly. At least there is some evidence to consider that. And I thought that, well, maybe this is actually the reason for the precession of the Mercury's perihelion. I don't know, it's just an idea I've had. Another interesting correlation, let's say, is the velocity of this interstellar wind is 26 kilometers per second. But this is the same velocity that we calculate for Oumuamua at infinity, mysteriously enough, let's say. And also another thing I've noticed is that at 26 kilometers per second, like, how long does it take for this interstellar wind to come from the edge of the heliosphere to the sun or back? And it takes 22 years, which is the solar magnetic cycle, which is, from maximum to another maximum and to another maximum. So the magnetic poles kind of change and then reverse back. So it's an interesting correlation, let's say. Okay, so let's talk about this mysterious Plasmascape thing. Now, first of all, I wish to introduce it as a general concept, so maybe as a term that you can use in your discussion. So I would say, like humans live on land, so we care a lot about our landscape, right? This is what is important for us. But celestial objects, they exist in plasma. So what matters for them is their plasmascape. That is the plasma structures around them, essentially, and their interactions with these structures, etc. So you might use this term, if you like. But not only it's the term that I propose to use, it's also the name of a tool that we've developed with these guys, me, David Johnson, Jim Wenninger, Chris Seeley, and David Negrau, although the last David haven't done anything yet, but I hope he will catch up. Okay, so this is the link that you can use to access our tool. although I wouldn't advise you to do it right now. Perhaps you can do it during lunch, because I've heard that the negative emotions such as like sadness and anger, they actually increase your appetite. So visiting our website might help you go through lunch. Okay, so what it is, it's essentially a tool for three-dimensional visualization of various structures that we have talked about previously, right? Firstly, the solar system, then the heliosphere with all those ribbons and belts, etc., then the local stars, then the interstellar clouds, then the local chimney, okay? But first, I'm going to show you a couple of screenshots, but first I'll show you this thing. So this was my initial idea for our logo, all right? So at first I arrived at stupid pun, which sounded like, well, since we have Plasmascape, I thought, let's have a Plasmascape goat, all right? So this is the idea. We have two Birkeland currents that kind of has two horns and a kind of twisted beard down below. So this is Plasmascape goat. But then we brainstorm, although it looks like a Playboy rabbit, right? But then we brainstormed a little bit. So this is what David Johnson came up with. This is what Chris Seeley came up with. But we thought, Chris, like, we probably shouldn't expose ourselves so obviously, Like, we should be a bit more discreet, Okay, so, but anyway, this is the thing we end up with. It was also designed by Chris Seeley. So again, you have two horns and a beard, and it's also cool that the red is kind of like a P, and blue is kind of like an S, so it's kind of like a Plasmascape, okay? So the motivation to do this thing, to develop this tool was, again, the idea that if we are to understand what's going on around us, at least we should know where the things are, right? So the first step we need to take is to map everything. And this is exactly what this tool is needed for. And we tried to implement those two important properties that I think it should have. The scalability, that is the ability to quickly change scales from the solar system to local interstellar cloud, etc., and see all the orientations simultaneously. And the integration, that means to be able to observe in the same 3D interactive environment, let's say the ibex ribbon, the orbits of planets, the solar rotation axis, whatever, right? There's a lot of possibilities, really. And it's actually a challenge to integrate all that and make it workable, let's say, okay? And we also wanted to make it available for mobile devices, so that also puts some constraints on the computing power that we can demand from your device, essentially. So we have, at the moment, actually this is taken from some older version. It should be better now, I hope, at least. So there are at least 5 scales available currently. The first 2 are for the solar system itself, because we have inner planets pretty much inside 2 AU, but the outer planets are from 5 to 30, so... but it's all essentially the same environment, so you can zoom in and out anyhow you want, but this is just for convenience, such a scheme. 3 is the scale of the heliosphere, so maybe we'll implement some like ibex ribbon there, things like that. 4 is the scale of the local interstellar cloud, again, that I've shown you. And 5 is the scale of the local interstellar chimney and this Gould belt around it, all right? So here's a couple of screenshots. Again, this is taken from some older version, so just keep in mind that we've started doing this literally a month ago, so don't expect anything super spectacular, right? But you can still use it, it's workable. So this is how it looks like. There's a whole bunch of, so you can see here, you can plot or at least summon the directions, like the solar apex, where the sun is moving, this ibex ribbon, interstellar magnetic field, and things like that. And I've also created a Facebook group mostly for feedback, so and kind of relevant discussions. If you have any ideas of what we should implement or what should be important, or if you have a theory of your own, etc., that might spark some discussion, then I would ask you to use that, but try to keep it relevant. Like, don't advertise condoms there or something. Like, this is not. And by the way, in this group, there's only me at the moment, as far as I understand, because I planned this to be announced here, so nobody knows about this thing yet. Okay, so to conclude this talk, I'll just briefly mention what I've talked about. So if we assume that the plasma currents play a significant role in the behavior of the interstellar environment of stars, planets, etc., we have to simultaneously solve these two problems, like theoretical problem. We have to derive from first principles how plasma should behave, or we have to adjust our principles if we see that it doesn't behave as it should. And we have to solve the observational problem, that is to, again, map everything to see where these objects are, how are they oriented with respect to each other, etc. And then I would say that Don Scott's model of Birkeland currents is actually a good take on solving this theoretical problem that I mentioned. So, yeah. And on the observational side, again, as I hope I've been able to show you, there are many peculiar effects and strange anomalies, strange correlations in alignments that might be explained theoretically through plasma processes that I've mentioned, again, like redshift, blue shift, refraction, and things like that. And there is more and more evidence of weird correlations that I've mentioned that I've found, for example, in motions and dynamics of observable objects in the solar system and in its immediate vicinity. And again, I've presented this tool that we've developed recently, this Plasmascape, so I hope it would be useful. We actually specifically aimed it at researchers, or at least people who are interested, right? So again, if you have any ideas how we can make it better, then go on and tell us, please. Okay? I also have a sort of a minute of self-advertisement. I also have a YouTube channel focused on more philosophical things, right? It's actually even more controversial than the EU. So it's called Eugene the Philosopher, if you're interested in this kind of stuff. And I also would have 2 informal talks during the symposium part, if you would attend. So I would talk about cosmology, like logics applied to logic applied to cosmology, and also the question of whether electromagnetism, as we know it in our labs, even work in space, because the conditions are very different. But we'll talk about that later. Thank you.